happens, this is just a summary of what happens with Le Chatelier and heat, okay? So if you increase the temperature of a system when it's at equilibrium, it favors the absorption of heat. And I'm going to write the other reaction, actually. To show you the opposite. Okay. So this reaction is endothermic. This reaction is exothermic. Okay? So in an endothermic reaction, what happens if we increase heat? The reason that I put heat as a reactant is if I increase this, the system thinks there's too much of it. I mean, the system doesn't think, but this, bless you, the system thinks there's too much of it, so it tries to get rid of that, and then it goes and produces products, okay? So if you increase a reactant, you're already at equilibrium, remember. You increase a reactant, there's too much of that reactant and it needs to be consumed, and then you go and form products. Similarly, if you're at equilibrium and you increase a product, then there's too much of that product and you'll have to go back to reactants, okay? So that's why I use heat as either a reactant or a product, because I just think in terms of reactions and products, and I don't have to worry about anything. Exactly. Yes, exactly. I don't even think about it in terms of this. Like I said, if it's an endothermic reaction, I put heat as a reactant. If it's an exothermic reaction, I put heat as a product. And then I just think of it, think of the temperature change in terms of reactants and products. We're going to do some examples. Yes. I don't want to publish. I can publish it. I'll publish it. I'll make that executive decision. It's there. It just needs to be published. I will publish it. Okay, so we already talked about, we talked a little bit about concentration. If there's too much of a reactant, we go and form products. If there's too much of a product, we backtrack and go form reactants, okay? Mm-hmm. In cases of changes in concentration or partial pressure, we do not change the value of K. Okay, so there's no change in the value of K. The equilibrium composition will change, meaning the concentrations will change at equilibrium, okay? So remember yesterday we were trying to find the concentrations of the equilibrium concentrations of products and reactants. Those will change if we shift, if we change concentrations when we are already at equilibrium, okay? And this is kind of what I was trying to say before, exactly what I was trying to say before. So if you increase a reactant concentration, or you increase a reactant partial pressure, there's too much reactant for the other reactants and products, and the system will respond by using up that excess and producing more product. Too much reactant, you make more products and you shift right. Too much product, you'll use up the products and go back to reactants and shift left. So shifting right means you go to products. Shifting left means you go backwards and go to reactants. The opposite is true of that second statement is just the opposite of what I said. Here's an example that we used yesterday, and this is a quantitative example of Le Chatelier. Okay, so I'll remind you of the reaction. Okay, So the reaction was normal butane isomerizing to form isobutane. Okay, so we mentioned that our K is going to be the concentration of the product over the concentration of the reactant. And we know that it's equal to 2.5, okay? So let's say we are at equilibrium, and our equilibrium concentrations are this. So the concentration of the isobutane is 1.25 molar, and the concentration of the normal butane is 0.50 molar. Now what we're going to do is we're going to change the system. We're going to add 1.50 molar of the normal butane, okay? So, in this case, we're going to write another ice table, and we're going to see what happens, okay? So, we've changed our equilibrium position. We've added something else. So, when we come to equilibrium again, our concentrations should change, right? Okay, so what is, did you have a question? I'm going to show you. So our initial concentration was 0.5, right? But we've added more. So this is our new initial concentration. This is a case where we start with something other than 0 in our product, because we were at equilibrium, okay? So this is a case where we're not starting with a 0 concentration in our product column. Does that make sense? We were already at equilibrium, and now we're shifting it, okay? So we're going to do the same thing we did yesterday. We don't know exactly how much has reacted and how much has been produced. But we're still going with the same convention that we're reacting, we're decreasing products, decreasing reactants, and increasing products. Yes? Right, because we're going to always go with the convention that we decrease our reactants and we increase our products. What I would do is I would still use the positive. I would still use the positive for reactants. I mean for products and the negative for reactants. I would still use that convention. You may end up with a funky answer, but the math will work itself out if you always go with that convention. Yes, I'm sorry. How do we know the stoichiometry is 1-to-1? Because I don't have any coefficients.